Well, hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step one inside as we jump into Chapter 7 in the Big Ideas Math Integrated Math 3 textbook. We're using sequences and series, and I think that's what this section's called, something like using and defining sequences and series, something like that. This is section 7.1, the introduction to it. Not just sequences though, you would have learned sequences back in IM1. I mean, if you were taught in that way in Integrated Math 1, it's okay if you haven't learned it, or if you don't remember it, we'll recall it back, but we're going to do it kind of quickly. You're now in IM3, your ability to not just recall things from the past, but pick things up is paramount to what we do here to learn series. That is not something you would have learned in IM1. So I'm going to jump into it right now. In the description section down below, you can find the PDF of this particular section, and you can find timestamps of the problem sets we're going to do up to number 61. But we begin with the lecture portion, which I'm going to begin right now. I'm going to move myself to begin with. We're going to use sequence notation to write terms of sequences. So that's stuff you would have used in the past, at least. Write a rule for the nth term of a sequence. Once again, something you would have done in the past. And sum the terms of a sequence to obtain a series and use summation notation. A series is a sum. A series is a sum, and that's one of the new target words that we have here. Summation notation is also, I think this is the part I'm going to lose some people because the symbol looks a little bit weird, and I get it, but we're just going to have to understand that it's a shorthand way of saying something that's significantly bigger. So hopefully I don't lose you there, or at least follow along with the solution guide video when we hit that part. But yeah, sigma, summation notation, I think these are the same thing. Summation notation, sigma notation. I always call them the same thing. I apologize if they're not. I pre-apologize if they're not the same thing, but I always call them the same. All right, writing terms of sequences. The core concept, a sequence is an ordered list of numbers. Now again, that shouldn't be anything new for us, that we have a list of numbers like this one, 2, 4, 6, 8, whether it's finite or infinite, the ... implies that it's going on forever. Finite implies that it actually stopped at 8. So just a list of numbers. When you have some sort of mathematical pattern, we might know it as an arithmetic sequence or a geometric sequence, things that will also pop up, obviously, in this chapter. A finite sequence has the limited number. Like I said, infinite has the infinite number, and we'll be using both. You can follow some sort of rule with it. So like I said, these are both arithmetic sequences. They have a common difference of 2, and you can write this one, a sub n equals 2 times n. If n represents the term's position that you have, and this is the first term, second term, third term, fourth term, we can substitute 1 for n to get the first term. 2 times 1 is 2, and 2 times 2 is 4 for the second term, 2 times 3, 2 times 4 for the third and fourth terms, and get those ones. And that's applied with either subscript notation or function notation. Either of those can use that specific thing. You know, maybe I should move myself over here. It looks like there's less for me to have covered. The domain can begin with 0 instead of 1. Sorry, I'm reading these off the bat as we see them. But you can start with 0 instead of 1. That doesn't mean you start with the 0th term. That means you start by substituting 0 in that instance. Hold on. I have to look at how this starts. Unless otherwise indicated, assume the domain of a sequence, though, begins with 1. I'm just going to go ahead and start with that. So when we're writing the first 6 terms of a sequence, we actually substitute 1 for n in these cases to get the first term and 2 for the second term, etc., instead of substituting 0 to begin with. And same with this one as well. Now, this is an arithmetic sequence. This is a geometric sequence. Just by nature of its appearance, this looks like a linear equation. This looks like an exponential equation. But you can also probably see when you look at these, they have a common difference of 2. And these have a common ratio of -3. And those are expressed with these numbers here. Common difference, common ratio. I might be over speaking on those kind of things specifically because we hit those probably more in the future sections. But I want to recap some things that you might have heard in the past and go, oh yeah, it's these things. Even if we're not making the equation itself right now, we will be shortly, I'm sure. And yeah, here it is, writing rules for sequences. When terms of a sequence have a recognizable pattern, you may be able to write a rule for the nth term of the sequence. Now, there are a couple things that these could get tricky depending on what the numbers look like, but based on what we might have seen in the past regarding patterns, we should be able to come up with something somewhere, even if it's from what we know from sequences before or from what we just did previously in IM3. Describe the pattern, write the next term, and write a rule for the nth term of the following sequences. We have this one where we go -1, -8, -27, -64. And then this one, 0, 2, 6, 12. Now, the first one is probably more obvious to you if you, well, actually, no, I take it back. That might not be obvious to you. You might be looking at what you're doing from one term to the next, in which case it might not be as obvious. From here, you might say, oh, you multiply by 8, and here you multiply by, oh, I don't really know, right? It's not as obvious. Or when you talk about subtracting, we subtract 7, and then 20, and then 37, and you're like, what the heck is that pattern there? There is a pattern within if you can determine what it is, but if you look closely at the numbers themselves, hopefully you can see and recall this is a perfect cube. This is 1 cubed, 2 cubed, 3 cubed, 4 cubed, or at least cubing the negatives, and that's what they're showing here. So you're cubing -1, -2, -3, -4. However, the n is not a negative number, so you have to insert that negative within, and it would look like this. A sub n equals -n cubed. How many will be that obvious? I don't know. They did that one for the example, so maybe it's possible we see it that way, maybe not. This one, maybe a little bit different. You can see if we're talking about, we would never say what we're multiplying by because there's a 0 in the way, but we can say what we're adding. We're adding 2 and then 4 and then 6, which is great if you wanted to find the next term. To me, it looks like the next thing I'm going to do is add 8, right? Give me 1 second. I just saw a message that I need to respond to. Hold on. Probably not the message I wanted to see right then, but I'll proceed forward. Okay. I got to get back my train of thought. Okay. This one. So the next thing I'd probably do is adding 8, and I'd get 20, and then add 10 and get 30 and things like that, right? But that doesn't get a rule for the nth term of the sequence. I want to substitute 1 into this thing and get 0 out. I want to substitute 2 into this thing and get 2 out, substitute 3 and get 6. So not as obvious this time. Let's see what they have to say, but there's something I want to say with this in a bit that has to do with the second difference, which is these are adding 2 each time from +2 to +4 to +6. It's a constant second difference, which means to me it screams quadratic. So let's see what they say about finding the actual rule from there so we can follow that pattern with them. You can write the terms as 0 times 1, 1 times 2. Okay, this works. 0 times 1, 1 times 2, 2 times 3, 3 times 4. That's something you might notice. A little less obvious there. But yeah, 0 times 1 is 0, 1 times 2 is 2, 2 times 3 is 6. I'm seeing another message. I'm going to ignore it. 3 times 4 is 12. So you're seeing that if this is the first term, second term, third term, fourth term, etc., we're multiplying 1 times the 1 times 0, the number before it, 1 minus 0. 1 times 1 minus 1, 2 times 2 minus 1. 3 times 3 minus 1, 4 times 4 minus 1, etc. And that continues forward. A little harder to come up with, but if you notice, that's, again, n minus 1 times n is what's happening. If you notice, if I distributed that, you're going to get n squared minus n, which means it was a quadratic. So my first go-to with that personally, I'd be looking at that as a quadratic first and saying, how can I use squaring something to come up with that answer? As in, like, 1 squared is 1, and that's clearly not the value here. But if I subtract itself, if I subtract 1, I get 0. I'm thinking in that terms. 2 squared is 4. Subtracting 1 would get 3, so it's not always minus 1, but if you subtract 2, you get 2. 3 squared is 9, minus 3 is 6, 4 squared is 16, minus 4 is 12. There's discovery to be involved. You have to recognize the pattern with it, and it's not necessarily easy, but if you know something about the nature of, again, this is cubics, this is quadratics, or some nature of them, you can probably find your way. So there's not any one-stop shop in figuring it out, but we are going to try and figure them out together, basically. Okay, here's an example on solving let me see this really fast. To graph a sequence, let the horizontal, I'm not going to talk about the graphing right now. We'll get to it when we actually do it. All right, solving a real-life problem. You work in a grocery store and are stacking apples in the shape of a square pyramid with 7 layers. Write a rule for the number of apples in each layer, then graph the sequence. So it still sequences as the first layer is on top, it has 1 apple, and then if you recognize that because it does the pyramid sequence down here, there's 1 on top and then 4 of them that make, imagine you have 4 apples and stick an apple on top. And then down below, I think it's 9, right? Boom, boom, boom. You should get 9 down below. Oh, actually, they show you right here. You notice that. Yeah, so you get 1 and then 4 and then 9, which to me sounds like a quadratic sequence in and of itself. You notice that, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, and that's continuing that pattern. So we can write it for all those terms in the sequence. We will have 1, 4, 9, 16, 4 squared, 5 squared, 6 squared, and 7 squared as those terms. Now, graphing it, that's why they mentioned this. I'm sorry. I didn't notice. I'm rusty right now. I didn't notice. I thought this was a part of this up here. No. This statement is a part of this down here. So let me read that again. To graph a sequence, let the horizontal axis represent the position numbers and the vertical axis represent the terms. So the first term is 1, the second term is 4, the third term is 9, etc. And they're going by that scale. So these are the n's and these are the a sub n's, the position and the values for those terms. We don't connect the dots and we don't have a 0th term either. We just have these specific points. So it's a quadratic. We mosey on forward. Okay, writing rules for a series. So this will be the brand new portion for you. A series is a sum of your terms when you add them together. It doesn't matter what kind of series it is. It could be arithmetic, it could be geometric, it could be Fibonacci, it could be cubic, quadratic, whatever it is. When you add them together, you have constructed the series. That value that adds the terms together. It's not just the list, it's the sum of the list. Now, a finite series specifically also for an arithmetic sequence will always have a finite value. It'll end and it'll become something. 2 plus 4 plus 6 plus 8 is a number. But what if I added 2, 4, 6, 8, 10, 12, 14, 16, and it kept going forever? I guess it would go to positive infinity, right? But you can use something called summation notation. I think that's also sigma notation. So let me keep that clear. Summation notation to write a series as well. And this is where things will look a little bit confusing to people because you use sigma. That's why I think it's also, here it is, sigma notation. Sigma notation uses the Greek symbol sigma. Everyone will call it E. At least when you see it for the first time. Mr. Robinson, you know that E thing that we do? Sigma? Yeah, that thing. I guess it looks like an E, sort of. It also looks like an M that's tilted over, if you think about it like that. You know that M thing? It's a Greek letter. It's a Greek letter, sigma. Sigma is used for summations of values. It is a symbol, just like anything else. It serves as a function, like square roots and absolute values and logarithms and sine and things like that. It does something to your numbers, but it does it in a very specific way. So how do you do the finite series 2 plus 4 plus 6 plus 8? Here's what's going on with this notation, and I know it's crazy, and I'm going to rewrite it. First of all, there's E, there's sigma itself. The bottom number is important here. We use this variable. It's a temporary variable, I, that we're going to substitute. We start with 1. This bottom number is what we start with by substituting into here. See where it says 2i? That means we're going to first begin by substituting 1 in for i, and we get 2 times 1. But that's not it. We are going all the way up to 4, and we increase by increments of 1. Now what we're going to add the result. So we do that 2 times 1. The next thing I'm going to turn I into is 2, and I'm going to add the results of that with this formula here, 2 times 2, plus, and now I increase I by 1 again, get 2 times 3, plus, and then I go up to 4. That's the top one, 2 times 4, and I'm done. So what this sigma notation thing does is it's a shorthand way of saying find the sum of the first 4 terms of the sequence using this rule. Find the sum of the first 4 terms of the sequence using this rule. You substitute 1, 2, 3, and 4 into there and you add them up. That's obviously, again, 2 plus 4 plus 6 plus 8, which is what they're talking about here. That's why they're talking about it. This is also the same rule, but this thing goes infinitely, so it doesn't just do the first 4 terms, it does the first infinite number of terms. So you don't go from 1 to 4 this time, you don't go from 1 to a billion, you go from 1 to infinity. And we can write it that way, and here's a shorthand way of saying that. I guess they're showing all that right here and how this thing is used and why that is. I just wanted to get a better, bigger building explanation onto it, and I hope that that kind of makes sense in how that's used. So we can write sigma notation for sequences, and I think we're about to do that in a second. We can use sigma notation to then write out a series and then actually be able to evaluate them as well, and we're going to do more with those formulas as a whole. So this one wouldn't have, I already mentioned, this one wouldn't actually have a finite value because it adds numbers forever and the numbers keep getting bigger. So in that case, it doesn't technically have a sum. And I know they didn't ask about that, but I just wanted to let you know. All right, writing a series using summation notation. They say write each series using it here. So what we're going to do is come up with, this goes 25, 50, 75, etc., all the way up to 250. Your goal is multifold. For 1, you do have to figure out the rule for this thing. what's happening from one term to the next, or by substituting in 1 for n or for I or whatever, how you get 25 and how you get 50. To me, it's as straightforward as you're multiplying 25 by the number. 25 times 1 is this, 25 times 2 is that. The next thing you have to do is figure out how many terms there are, because if we're going to use that sigma notation rule, we have to go from the first term up to the whatever number's on top. Now, I think to us, clearly you can probably tell 250 is 25 times 10, so it would be the 10th term. There are other ways that we can use formulas to determine that if it's not easy to find out. This one I think was easy enough, so we understand that this goes to the 10th term from 1 all the way to 10. And the rule is 25i or 25n. Whatever variable you want to put there is fine. If I put n here, that's fine as long as I put n here. They tend to use I as the temporary variable. I tend to as well, so we're going to stick to that. Sometimes they use k. Sometimes they use k. You can use whatever you want, but it needs to follow the same variable here. Anyway, so this is going to be the rule for this in sigma notation, because you are adding 25 times 1 with 25 times 2 all the way to 25 times 10, and that's where we get that. We didn't come up with the answer to what these add to. We came up with a shorthand notation for how to write this out. Next one, 1/2 plus 2/3 plus 3/4 plus 4/5. You have to remember this is, again, the first term, second term, third term, fourth term. So in terms of coming up with a rule, you have to ask yourself, how do I use 1 to get the numbers 1 and 2? How do I use 2 to get 2 and 3, 3 with 3 and 4? The denominator is always 1 more than the numerator. So if my first term literally uses, like, if I'm talking about this, I'm going to make this up without looking at the bottom. My first term is 1, so my nth term would use n. And then if this is 1 more than it, then this should be n plus 1. So I'm thinking of that as my rule, or they'll probably use I over I plus 1, right? Now this looks infinite as well because the ... and it doesn't show an ending. So we're going to go from 1 to infinity this time. So there's sigma notation. Where is it? There's that part. A sub I is I over I plus 1, where I goes 1, 3, 4, up to forever, up to infinity. So their rule is going to go from 1 to infinity of I over I plus 1, like so. Again, I know I might have lost you there a little bit. This is their notes. Hopefully, as we do more problems, you can start to build with it. That is sigma. That is not E. I want to start with that. And I don't know how far these notes go. I know we still have to talk about series stuff. So the index of summation for a series does not have to be I. Oh, I mentioned that. Any letter can be used. Here's them using K. So I guess they won't always use I. So I'll make sure to do that same thing. They use K. We can use K. Finding the sum of a series, now we're going the other way. We have sigma notation, and they want you to actually add them up. Notice this time, they go from 4 to 8. That means the first number we substitute for k will not be 1. It'll actually be 4. But they always have integer values here where this one's larger than this one, and we always count up by 1. So we're going to substitute 4, 5, 6, 7, and 8 for k, and we're going to add the result of each of them for this rule. So here's where they substitute 4. This is 3 plus 4 squared. Plus, then they substitute 5, 3 plus 5 squared, etc., all the way up to 3 plus 8 squared. And you actually evaluate it, right? You use the calculator, whatever you want, but that's these numbers added together. These are the terms of the sequence, at least from terms 4 to 8. These are those terms of the sequence. Now we're adding them and getting the result of that. They gave you a shorthand version of asking you to find that sum, which works out for me without having the list. We can generate the list ourselves. For a series with many terms, finding the sum by adding the terms can be tedious. I would argue that these 5 terms added together wasn't very tedious. It's a little bit of work, and we're going to have to do multiple ones of them. But what if you had to add 30 terms? That can be tedious. I'm not going to sit here and do that each time. They might force me. But there's some formulas I think they're going to say. Yeah, below are formulas you can use to find the sums of 3 special types of series. Now later we're going to talk about arithmetic geometric series formulas, probably not in this section. But here, the sum of n terms of 1. So if you add 1 with 1 with 1 with 1, etc., you're going to get n based on however many terms there are. If it's 10 terms, 1 plus 1 10 times is 10, right? But what if you add... Now, this one is saying the sum of the first n positive integers. That means you're doing 1 plus 2 plus 3 plus 4. And if that should make sense here as well that we're doing that actually, because you substitute 1 for I, and then 2 for I, and 3 for I, and you're doing this all the way up till whatever that last term is. It can be 100, it can be 4, whatever it is. Now, there's a rule for that. Doesn't look like they're deriving it. We may have to do it ourselves. I'm rusty on that, so I might struggle with it. But here's a formula you can use to plug it in. And obviously, we're going to see an example of that. And the first n positive, the sum of the squares of the first n positive integers. So 1 squared plus 2 squared plus 3 squared, all those numbers, 1 plus 4 plus 9, all the way up to whatever you want to square there. You can substitute this one as well. So I guess these are ones you got to remember or you got to be provided and just know how to use. But this is only specifically for those sets. 1 plus 2 plus 3 plus 4, 1 plus 4 plus 9, etc. It's not any quadratic. It is this very specific individual one. You could do, I'll wait for it. I'll wait to see if they do that. But you can do ones if they multiply, if everything's 3 times larger than it. You just can't do very other unique kinds of quadratics. Okay. How many apples are in the stack in example 3? Now, if you remember, example 3 was the one where you had quadratic numbers based on the row. The top row had 1, the second row had 4, the third row had 9. They were, and I think they won 7 rows, so they were the quadratic set, 1, 4, 9, etc., up to 49. So it was 7 rows. You're doing it up to there without actually doing 1 plus 4 plus 9. Let's substitute it in the formula. Which way is faster is up for debate, but here's the notation. From 1 to 7 of the first I squared terms, and you substitute n into there. N being 7 is 7 times 7 plus 1 times 2 times 7 plus 1 all over 6. That's this formula here for that n. And that's going to become 140. So 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 is 140. That's how many apples there are in it. Okay, and that's it for the lecture portion. I mean, it was long, and I stumbled across a couple things. My apologies for that. Let's start with the vocabulary and core concept check, numbers 1 through 4, and then we'll do numbers 5 to 61. Okay. What is another name for summation notation? Sigma notation. I say sigma notation most often. I don't think, because I see the Greek letter. I think of the Greek letter sigma, and I get that. In a sequence, the numbers are called blank of the sequence. I guess the terms, I think that's how they're saying it, the terms. I often tend to call the numbers themselves the term's value, and I call the other thing the term's position. Here they might call them the position and the terms. Compare sequences and series. Sequences are a list of numbers. Series is the sum of that list. So the sequences is separated by commas. It's like, 1, 4, 7, whatever. And the series would be 1 plus 4 plus 7, which you can evaluate and do things like that. We started sequences back in IM1. Series is the brand new one for you, which there will be more formulas to be had. Which one doesn't belong with the other 3? Explain. Telling you right now, it looks like, well, let's do this. Let's figure out if this set adds to 91. Basically, I think I'm going to assume these are both the same, because I'm going to assume these two are different because they look different. So we're going to figure out this probably adds to 91 and then see where that goes from there. So 1 plus 4 is 5 plus 9 is 14, 30, 55, and yes, 91. 55. So these are the same. Let's call those A's. So does this list add to 91 or does this list add to 91? It's pretty straightforward if you substitute these values in. Plug in 1. 1 squared is 1. Then plug in 2 and you get 4. Plug in 3, you get 9. That looks to be this list. I'm not putting ... as if it's infinite, but I'm saying it's the same list as this. This list, however, is 0 squared plus 1 squared plus 2 squared plus etc. all the way up to 5 squared. So this one's different. These are the same. This one's different because this is that list expanded out. This adds to 91. This adds to something less than. I guess it adds to 55, actually. Because it's 0 squared is still 0. All right, guys, we are going to go ahead and begin. So get everything ready that you need as I prep my stuff as well. Give me a second. Okay, I think I am set to go. We're going to go ahead and get started. Numbers 5 to 61. Here we go. In exercises 5 to 14, write the first 6 terms of the sequence. So this is getting you practicing what we do just by substitution. We begin with a sub n equals n plus 2. To write the 6 terms, we have to substitute values in. A sub 1 is 1 plus 2, which is 3. I'm not going to spend this long each problem, by the way. A sub 2 is 2 plus 2, which is 4. A sub 3 is 3 plus 2, which is 5. A sub 4 is 4 plus 2, which is 6. A sub 5 is 5 plus 2, which is 7. A sub 6 is 6 plus 2, which is 8. Okay, so the first 6 terms are 3, 4, 5, 6, 7, 8. If you don't see the pattern, I don't know help you otherwise, but in case, let me just go ahead and call it out. You add 1 to get to the next number starting from 3. The common difference is 1. Now, this is one of those things, if you start to learn things about arithmetic sequences, if you remember things about arithmetic sequences, you might know the number that's written here is the thing that you're adding from one term to the next, something we could figure out on our own. And it's a straight substitution of these numbers. So I'm not going to spend as long substituting those ones in, and if we recognize a pattern from there, we're just going to go ahead and start spelling them out. But if we got to substitute, we'll substitute. So on number 6, this is a sub n equals 6 minus n. If I substitute 1 into here, I'm going to get 6 minus 1, which is 5. Substitute 2 in there. 6 minus 2 is 4. 6 minus 3 is 3. And you can tell we're decreasing by 1 each time here as we do 6 minus 4, 6 minus 5, and 6 minus 6. And then we get from that 5, 4, 3, 2, 1, 0. Those are the first 6 terms. So we're decreasing. And again, your common difference there was -1 for an arithmetic sequence, and that was just how the rule worked. So again, a lot of these you can clearly do mentally. Number 7, I probably will do mentally mostly because it was covered in the lecture for when it comes to quadratics. And of course, we can do them in our head, right? 1 squared is 1, 2 squared is 4. These are a list of perfect squares here, 16, 25, and 36. So yeah, it's a substitution of 1 upward to 6 as they ask for those terms. And that's what I tend to do for most sets of problems. I'll actually do that. I'll ease into it as I go, and I hope that you get to pick that up. Now, these have function notation, but it doesn't change what you're doing. You're still, for example, if I want to find the first term, I'm still substituting 1 for n. 1 cubed plus 2, and 1 cubed is 1, and 1 plus 2 is 3, things like that. So I'm going to kind of cut that off and just write them out. So 3. 2 cubed is 8, plus 2 is 10. 3 cubed is 27, plus 2 is 29. 4 cubed is 64, plus 2 is 66. 5 cubed is 125, plus 2 is 127. And 6 cubed is 216, plus 2 is 218. Okay. Number 9, you have f of n equals 4 to the n minus 1 power. Again, I probably intend on doing these mentally, but hear me out as I go, okay? Substitute 1, that's 4 to the 1 minus 1 power, 1 minus 1 being 0, 4 to the 0 power is 1. Now, if you notice, I plug in 2, 2 minus 1 is 1, so we're doing 4 to the first power. We're just doing 4 to the next power, the next factor, the next power of 4, literally. You multiply another 4. So 4 to the first is 4, 4 squared is 16, 4 cubed is 64. Maybe you don't know what 4 to the 4th is or 4 to the 5th is. If you notice, though, we are multiplying another 4 than we did before. That's how geometric sequences work, and that's actually what this is. Whether or not you knew that, it's okay. We multiply by 4 to get the next one. That's 256, and multiply by 4, you get 1,024. So there's the first 6 terms of that one. A sub n equals -n squared. I'm only going to do a substitution for this really briefly just to remind you of how this thing actually works. You know, when you square a negative number, it does turn positive, but the bottom line here is we're actually not squaring a negative number. If I do a sub 1, I'm doing -1 squared, but if you follow my rule of 1 in doubt, use your damn parentheses, you might notice the parentheses go around just the 1 and not the negative symbol. We're squaring 1. You don't need the parentheses, but you're not squaring -1. You're squaring 1, and then you're making it negative. So that's -1. You square 2, and then you make it negative. You get -4. It's this list we had here, but they're all negatives. So we're not squaring the negative number, not unless this was written like that, right? So we're not squaring the negative number. So we'll get -1, -4, -9, -16, -25, and -36. All right. Number 11. I'm going to write it right here. N squared minus 5. Now, we take, 1, 4, 9, 16, 25, 36, and subtract 5 from them. So if you look at that list, you might know. 1 minus 5 is -4. 4 minus 5 is -1. 9 minus 5 is 4. 16 minus 5. 25 minus 5. And 36 minus 5. That's just going based off the pattern of the previous ones that we saw. It's not the negative versions of those, right? We're just subtracting 5 from the positive ones. All right, number 12, we have n plus 3 squared, quantity squared. So, this can be easier than plug in each number one at a time. If you notice, you are actually doing the number plus 3 before you square it. So 1 plus 3 is 4, but 2 plus 3 is 5, and 3 plus 3 is 6, etc. We're just doing 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, right? That's what we're substituting here. So I want to alleviate that a little bit. 4 squared, right? 1 plus 3 squared, and 2 plus 3 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared. If anything, maybe they're gearing you up for pattern recognition and what to do so we can write our own rules eventually for ourselves and what kinds of things we're going to have to do to make those rules. I anticipate that's probably part of what they're prepping you for. Number 13, it might be worth substituting some of these things in, especially if we have to do any fraction reduction. I don't know, but I assume we will. So let's at least do the initial list pre-reduction before we actually simplify that. So substitute 1, we get 2 times 1 over 1 plus 2. That's 2/3. And then substitute 3, substitute 2, you get 2 times 2, which is 4, over 2 plus 2, which is 4. So 4/4. Again, I'll reduce it in a bit. Plug in 3, you get 6 over 5. Plug in 4, you get 8 over 6. Substitute 5, you get 10 over 7. Substitute 6, you get 12 over 8. It looks like every other number, the even terms, we're going to have to reduce. So that becomes 2/3, 4/4 is 1, 6/5, 8/6 is 4/3, 10/7, and 12/8 is 3/2. When you look at this list, it's a lot more difficult to determine what, if they gave me this list and said, give me a pattern, that'd be hard to come up with. I would really have to look at the fact that, hey, if I get, I guess not a common denominator, but if I rewrite this with a different denominator, notice that was 3, 5, and 7, maybe I could turn this into some sort of 4ths and 6ths and 8ths, then I could probably determine the pattern off that. So not as easy when reduced, and I think that's another reason why it's good to show both of them. Number 14, last one from this set, we have n over 2n minus 1. Again, kind of a repeat of the last one, different numbers, but I'm going to write the raw form first before fraction reduction if I have to. So the first one is 1 over 2 minus 1. That's 1 over 1. The next one is 2 over 4 minus 1. 2 over 3 over 4 minus 1. 3 over 6 minus 1. 4 over 8 minus 1. Now, without me actually calculating, look what's happening. The top is obviously just the n value. We know that. The bottom values are odd numbers. 1, 3, 5, 7, 9, 11. I'll just kind of go straight to that. Nothing can reduce except 1 over 1 is 1. And I'm just going to write that one like that itself. So 1, 2/3, 3/5, 4/7. Maybe I could notice that one off the bat pretty well, but that's because nothing reduced. Okay, that's up to number 14. Let's do numbers 15 to 26, quite a bit. Describe the pattern, write the next term, and write a rule for the nth term of the sequence. If by describe pattern, they mean tell me whether it's, because this first one's an arithmetic sequence, that's what I'm going to do. I don't know if, did they state, hold on, I'm trying to fix this. Did they state arithmetic and geometric out loud in the lecture, or was I the only one who did that? I think I did. So they might be assuming that you remember how that works. If they did, I apologize because I don't remember. But here's what we're going to do. Unless they mean describe that it's infinite, but all these are infinite, looks like. So number 15, describe the pattern. I'm going to call it arithmetic. Arithmetic means it has a common difference, and this one does. You're adding 5 each time. They did say write the next term. The next term, which a sub 5, by the way, you would add 5 from the previous term, so 16 plus 5 is 21. And then write a rule for the nth term of the sequence. This is where you got to get deeper into that. Do you remember anything about arithmetic sequence rules? I think I have to get into this with you guys a little bit here. So an arithmetic sequence rule or formula that I would generally use for my students is this one. You take the first term and you add your common difference n minus 1 times. You can simplify it by then distributing that d into there. It looks like they're kind of doing that several times when they've made these things happen. So what we're doing here is to find the value of the nth term, you take the first term 1 and you add the common difference 5, n minus 1 times, and this would be an acceptable answer by IM1 standards or whenever you last learned this, so that would work. But what I've seen them all have previously were simplified versions. So if I distribute 5 into here, I get a sub n equals 1 plus 5n minus 5, or a sub n equals 5n minus 4. That's a rule for this thing, so I can substitute values in. Again, I could have done it here, but this is more simplified. Substitute that into there and get that rule. And that is number 15. You know, they might have mentioned arithmetic sequence if they're saying see example 2, but I don't know if all of them are arithmetic or geometric. We'll find out shortly. They could be quadratic or something like that, obviously, right? Number 16, 1, 2, 4, 8, etc., and so on. This is a geometric sequence. This has a common ratio. A common ratio meaning you're multiplying some same number from one to the next there, multiplying by 2. So if you want to find the next term in the sequence a sub 5, you do 8 times 2, which is 16. And a geometric sequence rule that we tend to write does use that n minus 1 like this, to the times r to the n minus 1 power. I guess these are things they're assuming you would know from the past or from the examples that you saw that we can use. So if we use this setup for this, and I'll maintain it with the n minus 1, you will have a sub n equals, the first term is 1 times the common ratio of 2 to the n minus 1 power. Now, as you know, 1 times anything is just that number, so the one version of simplification I can do is maybe write it like that. 2 to the n minus 1 power gets you your next value, and that's how I would go with that one there. Okay, and by the way, I didn't substitute this one to double check for either one, but I could. So 5 minus 1 is 4, 2 to the 4th is 16, that works out. 5 times 5 is 25, minus 4 is 21, so that checks out. It might be worth me checking those if I remember to. Number 17. We have decimals, but that doesn't change the fact that this appears as an arithmetic sequence. It has a common difference, and if you don't know how to determine common difference, common ratio, and I'm not saying that this one's hard to do, but if one was difficult to do or you wanted to test it, subtract a number from the one before it. This minus this is 0.7, this minus this is 0.7, and this minus this is 0.7. So this is an arithmetic sequence with a common difference of 0.7. And if I add 0.7 again to get to the 5th term, I will be getting 5.9. So to write the rule for this sequence, we can take the first term of 3.1 and add 0.7, this n minus 1 times. When we distribute the 0.7 into there, we're taking as 0.7 away from 3.1, and we get 2.4. So we get 0.7n plus 2.4. It might be worth mentioning at this point. I don't know if I'm going to use it this way, though, because I feel like I need to talk the talk in both ways. There is a way to write this one out straight up without starting with this one and distribute, if you know what the 0th term is. And I think that's one part they mentioned in the lecture, that you can apply some 0th term to this by subtracting 0.7 from this number to get what the term would have been before, because that's what's showing up here, 2.4 in this one. And in the other, I'm talking about arithmetic sequences only. And in this one, if I subtracted 5 from this one, I would have gotten -4, which is this number here. So you can do that if you'd like to, just by figuring out what the term before would be. And that's clearly what we're doing here. That's why this -5 shows up here like that. And that's why the minus 0.7 shows up here like that. So that's what we have in those if you want to do that a little bit more quickly. Or, of course, you can use this answer. That's fine. Okay, number 18. Not clear as day what it is. I'm going to first check and see if this is an arithmetic sequence. If not, I'll check on geometric. So we have 9, 16.8, 24.6, and 32.5. You add 7.8 here. Is that plus 7 point? Yeah, this is, you're adding 7 point each time. So 7.8 each time. So this is an arithmetic sequence. Common difference of 0.7, 7.8. So if I add another 7.8 to 32.4, you would get 40.2. 40.2. Now let's try what I was stating before. The 0th term would be subtracting, there's no real 0th term, it's a hypothetical one. Subtracting 7.8 or adding 7.8 to something to get 9. That would be 1.2 right here. So for 1.2, this is a sub n equals 7.8 is the common difference, and 1.2 is the 0th term that we use there. And I can jump straight into it from that, and it actually works out. And so that gets us our value. So that's another version of that formula. Basically what I'm doing, if you understand the first set is taking, the first one we were doing looks like this. That's a formula. What we're doing right now is this. We're doing this equivalent of that. We're taking the 0th term instead of the first term. Kind of your choice on how you want to get to it, and I don't know who I'm talking to with this, meaning your teacher told you how they want to see it, and I'm presenting both of them to you. Number 19. The numbers are going down, and because it goes from positive to negative, that means it's definitely not a geometric sequence. So my guess is this will be arithmetic. We'll do a test to confirm. And then we got to obviously find the common difference along the way. According to this, it looks like we're subtracting 1.6. And you'd be right. Subtracting 1.6 from one value to the next indeed makes this an arithmetic sequence. And I hope that when they say describe the sequence, me saying arithmetic or geometric is correct. Because so far they have been one or the other. So I'm living with that. And that's how we're coming up with our rule anyway, right? Subtracting 1.6 from negative 0.6 is negative 2.2. Okay. So we got a negative 2.2 there. And, oh, that's not the 5th term, though. They said the next term, and that's 1, 2, 3, 4, 5. This is the 6th term. Did I make that mistake for this one? 1, 2, 3. Nope. So this is the 6th term, but it is the next term. Let's try that 0th term thing again. Let's add 1.6 to get the 0th term, which is 7.4. So now your common difference is negative 1.6, which multiplies by n, plus the 7.4 right there. That's where that rule originates. I promise to do the distributing one again if we find another arithmetic sequence, but I just wanted to call attention to how that thing works. This one doesn't look arithmetic because the alternating signs. It appears geometric. We have number 12. Actually, that's not geometric. I don't know how to write a rule for this. Oh, I do. I have to think about it. I have to think about this. But this is not a geometric sequence. The thing is, though, I don't know what to call this. Okay, the reason I thought it would be geometric is because the signs alternate, which means you multiply by a negative to get from one to the next. So that was my first thought. But it's not. I know what I want to write as an answer, but I have to explain it. I just don't know what type it is. I don't know how to tell you the type. This has an arithmetic nature to it, more so than geometric. That's what I'm going to begin by saying. Now, when you look at this, you might say negative 4 plus what is 8? Oh, it's plus, I don't even know, plus 12. And then right here, 8 to negative 12 is negative minus 20. And then here it's plus 28. And that gets a little weird. Maybe you can tell something that you're doing from one term to the next. I kind of can. I don't know how to give it a name for what it is. I'm going to say that straight off the bat. I don't know how to say what type it is. But let's say these were all positive for a second. 4, 8, 12, 16. That would be arithmetic, right? And this rule would be, we do, it's a common difference of 4. The 0th term would be 0. Right? So in a way, you could just say a sub n equals 4n. By the way, the next term on this, let's write that out as well. The next term is negative 20, if you agree with that, because the sign would change. So a sub 5 is negative 20. And here is a rule for what's in blue, but that's not the rule for what is in black, right? If we were talking about this would be the rule. I want to use that rule, but I want the numbers to switch signs every time. What I want to do with this is I want to multiply it by negative 1 here, but then positive 1 here, and negative 1 and positive 1. And what better way to do that than to raise negative 1 to odd powers versus even powers? Negative 1 to the 1st, 3rd, 5th, 7th, 9th power is just negative 1. Negative 1 squared into the 4th power, 6th, and 8th is positive 1. And if these are the positions, this is position 1, 2, 3, 4, etc. If I raise negative 1 to that power, it'll be negative. Negative 1 to that power, it'll be positive. And negative and positive. And these are the positions. So let's do this. A sub n is 4n times negative 1 raised to the nth power. That's the only way that I can think about how to do this one with you that makes sense to me. And you have to have the negative 1 in parentheses, but that'll work out. This is not an arithmetic sequence because of that, but it has the earmarks of one. And since we have 6 more problems, I hope the next 6 aren't as tricky as this one would have been to explain. But see if this works. Let's substitute 5 into here. 4 times 5 is 20. Negative 1 to the 5th is negative 1. 20 times negative 1 is negative 20. So it does work. I mean, it works. It's just not arithmetic. So I don't know how to describe the type. It's a special type. It's a special type. It's arithmetic geometric is what it is. I don't know how to describe the type. I'm sorry. Number 21. This looks easier. 1/4, 2/4, 3/4, 4/4. Now, what's interesting about this is they did not reduce the fractions for you. It would have been really, we would have figured it out, but it's going to be interesting if they decide to reduce fractions later, if they called it 1/4, 1/2, 3/4, and 1, etc. This is not as obvious. It would become obvious if we know how those numbers work, but that one's not as obvious. The fact that they didn't reduce them helps us tremendously, right? We're adding 1/4 each time. Starting from 1/4, but we're adding 1/4 each time. So this is an arithmetic sequence. The 5th term, the next term, is 5/4, and I'll write it as an improper fraction. And my sequence is 1/4 n. Now, if 1/4 times n. The 0th term would have been 0. 1/4 times 1 is 1/4, 1/4 times 2 is 2/4, etc. That's how we write it. You can also write it as n over 4. Maybe that was more obvious to you, that you can say n over 4. That's fine. I kind of prefer this one. It truly shows the common difference with that number there than this one. But they both work. Number 22. Once again, doesn't look like they're reducing fractions based off the 5/30ths. And once again, it's probably helpful for us, but I think it would have been nice to come up with what the thing was. So I'm really curious to see if they ever do reduce the fractions and make us determine what it is. We'll see. But this one here has some clear as day notions to them, right? The bottom, oh, you're adding 10 each time. The top, oh, you're adding 2 each time. There's kind of something to that. They both have arithmetic sequence natures to them. It's almost like you can come up with 2 different formulas for them at once, and I'm actually curious to do it that way the first time, and maybe next time we can do something else with it. As in, like, I'll make this one blue and make this one green. Let's treat them separately for a moment. Is that okay? We're adding 2 each time on top. That means when it comes to the 5th term, the next thing here will have 9 by adding 2 each time. And then we're adding 10 each time on bottom. That means the bottom will be 50. So instead of thinking about, oh, gee, what am I adding from one number to the next here? Because listen, I don't even know if it's arithmetic or not. I guess we can't guarantee that it is. This is just a special type. And we're just saying, hey, we're adding 2 on top. Hey, we're adding 10 on bottom. And I just came up with the term based off that, right? Not, oh, we're doing this from this one and this one like that as a whole fraction. So that's how I wrote that. Now, as 2 separate terms, I'm doing this temporarily and then we'll combine them. The top one, you have a common difference of 2. And you are, your 0th term would have been -1, right? And then for the bottom one, you have a common difference of 10, and your 0th term would have been 0. So as a collective whole, those aren't the answer, but as a collective whole here, your rule would be 2n minus 1 all over 10n. And you can just write it as such and you'd be good. So we have this 5th term, this rule, and that should continue forward for all the different values that we do. Doesn't look like they wanted to reduce the fraction, so I won't either. Number 23. And we're not even at the series stuff yet. So these sequences aren't probably things you would have done in IM1. So they're really conditioning you for pattern recognition, and I'm cool with it. And again, I do believe, I haven't seen the chapter names thing in a long time, but I do believe we hit arithmetic sequences next, or whatever, arithmetic next, and then geometric specially next, and probably infinite geometric and things like that. But that being said, these are just any type that we're doing. Now, this one is not just any type. This is specifically a geometric sequence. The top is unchanged. No, I take it back. It's not geometric. I take it back. It's not geometric. I apologize. I thought this was ×2 or ×3 or something like that. Again, it's a special case. I don't know how to identify these cases if they don't have a specific name to them. I apologize. I don't have a name for these. But, the top is unchanged. Literally, when it comes to us writing, well, first of all, the 5th term is you're adding 3 on the bottom. So this is 2 over 15. As far as the rule goes, the top is literally 2. There's no n involved. It's unaffected by n. It's a constant. The bottom is affected by, well, you're adding 3 each time. You're adding 3 each time. And the adding 3 each time means you get to multiply 3 by 1 here. 3 times 2, 3 times 3, 3 times 4. So it's 2 over 3n. With the n being on bottom, that would be our rule. So the fifth term, 2 over 3 times 5 is 2 over 15. Are these the exact ways to state the answers? I don't know. Are those the answers? Yes. Is that the exact process for which we should govern them? I don't know. To me, yeah. You come up with your own way, right? The solution guide here that I'm doing is I'm giving you talking points for why you might write something the way that you do. And that way you can discover for yourself. And that's what I'm doing here. Number 24, once again, fractions aren't reduced, so we can kind of look at top and bottom separately, and I would keep doing that. I wouldn't change that unless it's a specific type of sequence, arithmetic or geometric. In this case, it still isn't, but the bottom and top can be treated like their own forms of arithmetic sequences, right? So on this top one, you're adding 2 each time. Well, first of all, fifth term. Adding 2 each time means the top would have 10. Adding 1 on the bottom each time means we get 7 for that one, so there's the next term. And that's what we're doing. We're adding 2 on top each time. This is 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times n. And on bottom, starting from 3, we're adding plus 1 each time. So a common difference of 1, that's 1n or n. The 0th term would have had a 2 here, so I'm going to say plus 2 like that. You have to remember we substitute 1 the first time to get the first term. So 1 plus 2 gives us 3, and then 2 plus 2 gives us 4 like that. So this being the 0th term totally makes sense, and that should be our rule. Okay, 2 more in these sets, numbers 25 and 26. This one I can't call out immediately. Let's process it. 2, 9, 28, 65. Oh, I do see it. And it's just because when I saw the 65, and then I saw the other ones tracing backwards. Okay. It's neither arithmetic nor geometric. But it's not that the arithmetic doesn't have good value to it. Only because I can see what it is, I'll know what to say. If I didn't, I don't know if I would know what to say for you. But we're adding 7, and it's important for me to say this. We're adding 7. Maybe you notice it as well. We're adding 19, and here we're adding 37. I don't want to be wrong. Here I think we're adding 37. These don't have a common difference, but the second difference, oh, and you won't be able to see this for yourself. Shoot. They're kind of mean by this. This is adding 12, and this is adding, what is that? From 1937, that's adding 18, and from here to here, we're adding 6. This is a little bit mean because it doesn't show you the next thing would also have the same common difference. I'll tell you what. This is tough to say for now because they didn't give us this, but if I got to add 6 to get how this would, it's basically that the third difference is common. The third level difference is common. So here you would have added 24 to this difference here. 37 plus 24 is 61. So we're going to be adding 61 to 65 to get 126. This would be the next term, basically, right? That's what we're referring to for that. This would be the fifth term. And I'll talk about what that is, see if we can confirm it after. This is our a sub 5. So the reason I wanted to bring this up was to show if your third difference is constant, then you have a cubic. Now, we hadn't been mentioning what these other ones were before, but I'm going to call out this very specifically as a cubic type. Mr. Robinson, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. These are not the cubics here. Yeah, but this is 1 more than 1. This is 1 more than 8. This is 1 more than 27. If you notice, this is, again, 1 plus 1, 8 plus 1, 27 plus 1. 4 cubed is 64, and that's 64 plus 1, and this is indeed 5 cubed plus 1. You're cubing your value, again, 1 cubed, 2 cubed, 3 cubed, 4 cubed. You're cubing your term's position that you have and adding 1 to it. And I only recognize it from the 65, saying it's close to 64, and that's close to 27 as I trickle backwards. So your rule, I'm going to write here is n cubed plus 1, and that was just recognized through that thing. They didn't give you enough to show the constant difference, but because I knew it was cubic, I knew this had to be true to build into that answer. Next time, we could just try and recognize it for what it is, and I'm fine with that. I'm fine with that. I just wanted to show how I knew it wasn't arithmetic, geometric, things like that. The next one, actually has the same principle involved, and in fact, we might need to use it for this one because I honestly don't know how to write the answer for it yet. So let's come up with it shortly. Give me a moment. Okay, now, only because I saw what we're doing from one to the next. We're adding 3, and then 5, and then 7. That might ring a bell to you that, first of all, the next one will be adding 9, right? So the next term is 25.2, as we do 16.2 plus 9. But the second difference is constant because we're adding 2 from 3 to 5 and adding 2 from 5 to 7. If we're adding 2 each time, that does make it a quadratic sequence. The question is, how do you come up with the rule? And that's where I'm at pause and I'm thinking about it. And I don't have anything off the bat. But if it's a quadratic, that means I can square. Remember, you have to think about squaring something to get your values out as, oh, I know what it is. Oh, this is kind of obvious. We have to square 1 somewhere within this and square 2 somewhere within this to get the things. And that's where it's going to show up. You know what 1 squared is and 2 squared is? That's 1 and 4 and 9 and 16. I don't know why I didn't catch on to that. I'm sorry. And this is 1 plus 0.2. 4 plus 0.2, 9 plus 0.2, and 16 plus 0.2. And that's why this is 25.2. It's 25 plus 0.2. Okay, that was a lot easier than I thought. Now, was it going to be that easy? I don't know. But it was, so we get to do it. So a sub n is you square your position, n squared plus 0.2. And that would be that answer there. Okay, there was our 15 to 26. Nothing else on the bottom. Let's move to the next frame. Okay, which rule gives the total number of squares in the nth figure of the pattern shown? Justify your answer. Number 27. The first term has 1 tile, the next term has 3, and this has 6, and this has 10. Are those the triangular numbers, I think? Is that what they're called? 1, 3, 6, 10. Let's see which one follows that. 3n minus 3. 3 times 1 minus 3 is 0. It's not a. It's not just n. It's not just 1, 2, 3, 4, etc. 4 times 1 minus 5 is negative 1. So that one doesn't work. 1, it must be this. 1 times 1 plus 1 is 1 times 2. Divided by 2 is 1. That works for that. 2 times 2 plus 1 is 2 times 3, which is 6. Divided by 2 is 3. It seems to be this one, part D. Now it says justify your answer, so I got to do a little bit more here. I already kind of ruled out how it's not all the other ones. So for A, your A sub 1 value is 0, so no. For B, your A sub, literally, I'm just substituting A sub 1. A sub 1 is 1, sure, but A sub 2 is 2, and that doesn't work. For C, I guess you have to try them all first. A sub 1 is negative 1, so that doesn't work. And then for D, it does work out because A sub 1 does give you 1, A sub 2 does give you 3. I'm going to trust it, and I'm going to show you how else we can determine this. A sub 3 is 6, and A sub 4 is 10. You know, one other thing that we're going to bring up over time, if you recall, if you saw the lecture portion, this is actually the sum of the first n positive integers. So this list of 1, 3, 6, 10, 1 is the number 1, right? 3 is 1 plus 2. 6 is 1 plus 2 plus 3, and 10 is 1 plus 2 plus 3 plus 4. And if that wasn't obvious alone by those numbers there, you can look at the tiles. This is 1 plus 2 plus 3 plus 4, etc. So there are a lot of different ways we could have done this, whether we tested numbers by plugging them in, knowing what this formula represents and how the tiles go with it. A lot of different ways we could have spoken on it, and that's just what I went with. All right, number 28. Which rule gives the total number of green squares in the nth figure of the pattern shown? Justify your answer. This has a couple things that I could look into to talk about it, but we can also obviously do test values to figure it out and see if we can justify it from that. Now, the first term has 4 of them, so that would not apply to A. If I did A, your A sub 1 would actually be 0, so that's no good. It's not A. If I did B, that's also no good because 1 squared over 2 is 1/2, so it's not B. C so far would hold up for the first term because A sub 1 is 4 times 1, which is 4. A sub 2, if you calculate that as 4 times 2 is 8. Are there 8 tiles? 3, 6, 7, 8. Yes. So there are 8 tiles there. And let's see if the third one works out so we can confirm that. Otherwise, well, it's not D, so it must be C. A sub 3 is 4 times 3, which is 12. And there are 4, 8, 10, 12 tiles there. So it looks like it's going to be C. It's going to be C in that case. If you did D, you would find out A sub 1 is 3. And that also doesn't work out. So, yeah, you know, eliminating some of those ones, C ends up being your answer. We'll go ahead and take that for what it is. All good. Okay. Number 29. Modeling with mathematics. Rectangular tables are placed together along their short edges as shown in the diagram. All right, so see, if you see the picture, it kind of becomes, you know, I was going to say the Last Supper. I don't think there were people facing us on the backs here, but the table gets longer as the ends stay the same, a constant one chair here, and we grow this way. How much, we'll figure it out in a second. So rectangular tables are placed together along their short edges. Write a rule for the number of people that can be seated around end tables. Then graph the sequence. So let's count the chairs. These two at the ends, and then we have 2 plus 4. So there's 6 here. And then plus an additional 4 here is 10. So if you notice, these 2 here, those 4 there, plus a brand new 4, plus another brand new 4 here is 14. So this ends up being our list on number 29. 6, 10, 14. We're adding another 4 each time, which makes it arithmetic. So what do they want? Just write the rule. They do state graph the sequence. I apologize if they asked us to state graphing the sequence before. I don't think so. Your rule, let me go back to the way that we did it before. You start from the first term and add 4 n minus 1 times. This could be your rule. If you simplify this by distributing the 4, though, you get 4n plus 2, like that. Which just goes to show if I subtracted 4 from here and removed these 4, you're just left with just these 2 and, you know, Lady in the Tramp style, kind of something like that. Or I guess just any dinner date where you should face the person you're sitting across. Anyway, they are asking you to graph the sequence. So let me grab graph paper for this. Let me. I'm going to makeshift this one because this should be first quadrant values only, I guess, especially if it's word problems. So I'm going to take this guy and just take the first quadrant out from it like that. Apologies, I'm makeshifting it. And we probably have to change scale. Graph the sequence. I don't know how far off we have to go. Maybe anything I can fit. But this, let's go by tens? Let me think about it. How high would this go if I went 10, 60? Let's go by 5s. Let's go 25 here and 50 here and just kind of plot what we can fit. So the first term is 6. That's, you know, this is 5. So 6 is a fifth of the way up there. This is 10. And then 14 is 4/5 of the way up there. And then it keeps going. So just plus another 4. So 18, 22. Were we supposed to write out what the other ones are? I don't think so. So I'm just saying them out loud. 26, 30. And it's linear, right? 34, 38. Oh, yeah. Oh, this is perfect. I was thinking we were adding 6 each time. Yeah, going by 5s was perfect. 38 and 42. Now, does 42 work for the 10th term? A sub 10 would be 4 times 10 plus 2. That is 42. So, yeah, that does work out. And there's my graph. Okay, number 30. An employee at a construction company earns $33,000 for the first year of employment. Employees at the company receive raises of $2,400 each year. Write a rule for the salary of the employee each year, then graph the sequence. Okay, this here, you could either write the list. We might have to write the list for the graph, but you don't need the list for the rule. You have the information for the rule. Your first term, the first year, is $33,000. Your common difference is $2,400. They're saying the next term is $2,400 more than the term before it. That might be important for us to write the list of numbers so we can graph it properly. Maybe. I'm going to try and come up with like different means of making sense of it in my head, I guess. But the rule is spelled out for you there then, right? Your nth term is the first term plus the nth plus the common difference times n minus 1. Now as I distribute like that, we will get a sub n equals 2400n plus 30600. Did I do that right in my head? I think so. So this would be our rule for this based on the nth term is the number of years, right? With this, the 33,000 being the first year. The nth term being the number of years, and then the value being how many dollars you have out from it. So let's move these over here. Let's copy paste this graph thing again and kind of try and come up with these values. I think I'm going to do them mentally, guys, if that's right. For the 33,000, how high will these things go up? Let's go by... These don't go up very high off of that. I don't really want to graph this one. You know what? Let's come up with what the numbers are, but I'm going to use the calculator for it. So check this out. We're going to get through this using... Oh, I have to reset this. Using the equation that we have, we'll do 2400x plus 30600. And let's just go to this table. Remember, we start with 1, where we have that 33,000, right? So I'm going to probably copy and paste these numbers. And they didn't really say how far down to go to. But, sorry, I'm just kind of, I'm getting these numbers. Give me 1 second. I'll at least go down to 10 and kind of see how things go. So, give me a moment. Okay, there is an 11 on what I copied and pasted, but that's okay. We'll ignore it. Okay, so going back to here, this is the list. And let's get rid of the 11. Now it's bugging me. So we got to go up to 54,600. So we got to go from, I got to be able to fit 5,500 on there. 55,000. If we go by 10,000, 5,000s, then this can be 25,000 here, and this would be 50,000 there, and that should be close to what we get there. Now, the problem is that there's nothing down here at all. 33,000 actually starts right there. Oh, wait, not even there. This is 30,000 and 35,000. So 33,000 starts about right there. 35,400, not quite high up from 35, so I'll do that. It's actually good that I got these numbers. I wouldn't have wanted to do the math here. 37,800 is a little more than halfway up to that. These should be arithmetic, by the way. This should actually look a little more linear than so far I've made it. But 37,800 is just a little more than halfway. 40,200, a little bit like that, again, in a linear fashion. 42,600, just a little more than probably halfway up like that. Again, following the path. 47,400. Just under, wait, hold on. Where would we be? 42,600. Oh, 45,000. I missed that one completely. 45,000. 47,400, just under that halfway mark. 49,800 is about right there. And then we're kind of creeping up and past. So 52,200. Sure. And then, yeah, that one. So following a linear path, plotting the points. We're not connecting the dots. And that'll be it. Okay. Write the series using summation notation, which is also sigma notation, on numbers 31 to 38. Okay, so, excuse me. Our goal is twofold. Come up with how many terms there are, and come up with a rule for each individual term in this set. They're not asking you to evaluate this result. That would be actually pretty easy to do for this one. But they're not actually asking you to come up with a result. Now, there are 5 terms, so that's the first thing I want to pull out. N is 5. When it comes to the general rule for this thing, as it's an arithmetic sequence, first term is 7, common difference is 3. You can use this version of the rule, or you can simplify it. I'm going to do this shorthand, 3 times n, 3 times -1. This is 3n plus 4. So the way I want to write out this rule will be as follows. I'm going to use that sequence rule. I'm going to use I instead. The book tends to use I. Sometimes they use K. I don't know. But we're going to go from the first term to the 5th term of the rule 3n plus 4. Oh, 3i plus 4, excuse me. 3i plus 4. Now, you would have had to have followed the lecture portion with me to know what the heck I'm doing with that as a whole. So I apologize if you didn't watch that portion. I will try and explain them more as we actually do the summation notation portions. But this sigma lets us substitute 1, 2, 3, 4, and 5 into I, and it allows you to add those terms together. So that is what we're doing with it, and that is how those come to be. Number 32 also is an arithmetic sequence given a common difference of 6, the first term being 5 there. So we have 5 plus 11 plus 17, 23, and 29. So once again, also arithmetic. There are 5 terms. My rule, I'm going to go the quick way this time with the 0th term. I have a common difference of 6, and if I subtract 6 from 5, I get -1. So there's the rule I can go off of there. So my sigma notation goes from, that terrible sigma, my sigma notation goes from the first term to the 5th term, given the rule 6i minus 1. Now, is it important that you use parentheses around this? Actually, it is. For anything that has multiple terms, it's important to say that this quantity is applied for the thing. If I didn't have parentheses and just, did the sigma thing, whatever, and had 6i minus 1, that means it only applies to this, and then you subtract 1 after the entire thing, not for each term. So yes, it's important that you do it for that. All right, number 33. Number 33 does not appear to be an arithmetic sequence. It, in fact, appears to be a quadratic sequence, because what I'm noticing here, and I don't know the rule yet, but what I'm noticing here is we're adding 3 and then 5 and then 7, which means that common difference is a common difference thing. The second difference is constant, adding 2. So it is quadratic. So there are only 4 terms. Keep that in mind when we're doing this. So we are going to go, when we write this whole thing out, it'll be from some I equals 1 to 4. There. My rule I need to write, I have to think about it. It's some sort of squared thing, right? If I did 1 squared, this might just be something plus 3. 1 squared plus 3 is 4. 2 squared plus 3 is 7. 3 squared plus 3 is 9. 4 squared, yes. So did I luck into that? I did. I guessed and checked. And that's what it was, n squared plus 3. So this will be I squared plus 3 for this one. And that's how we come up with that rule. Okay. See, I think that's why it was so important that they did these ones to begin with. These ones right here, they really get you in the mindset of different kinds of things that you'll have. They had an n squared minus 5. We just did an n squared plus 3, right? So I think it's really good that they did have those ones to begin with, so your brain can start thinking in those ways. Number 34. 34, if you guys notice, and I'm just going to say it out loud this time, we're adding 3, then 5, then 7. It's once again a quadratic, so we have to come up with another way of coming to terms with how that works. I'm going to guess it's another n squared kind of in a plus or minus constant kind of thing. So there are... Oh, shoot. Hold on. Time out. Let's go back to the previous problem. This was not 4 terms. This had a plus ... on it. I didn't copy it right. So there's an infinite number of terms. That means here we go infinitely on here as well. My apologies. Totally. This one's also the same. So the next, these 4 from 33 to 36 are all infinite. So we have an infinite number of terms. We're going to go from the first term to the infinitieth. Sometimes they use the letter K. So this time I'll use K in its place. So from 1 to infinity. Now, it's a quadratic again, because what I said, you're adding 3, then 5, then 7. The second term is constant. The second difference is constant. This rule here, if it's a quadratic, let's try and square 1. 1 squared minus 2 is -1. Is 2 squared minus 2, 2? Yes. 3 squared minus 2 is... Yeah. So this looks like there's a minus 2 involved. I think they're keeping it pretty simple. So here I'll put k squared minus 2. If you missed the lecture portion, you might say, Mr. Robinson, why aren't you using n here and you're using something else? I think I have seen them use n, but if you're coming up with a rule here, what you want to do here, and this is from my computer science background of programming, what you want to do here is assign a temporary variable that doesn't interfere with the variable that you had previously. You don't want to override something that you have in a permanent affixing value in with that one. Why do they choose I and K and stuff? I don't know. Normally I, J, and K, so we haven't used J yet. Normally I, J, and K tend to have their own, like they use them for vectors a lot, and then they use them for matrices or something. No, is that for vector? I don't know. Like they use them in certain ways. So why? I don't know, man. I don't know. But I guess don't use n if you're going to use n for the other part, is what I'd say with that. Number 35 is also infinite, but this appears to be geometric in nature. Now, it's been a moment since we've seen a geometric of anything, and I think this is our first geometric series. Now, we're not using a geometric series formula that you would know, but we're using geometric sequence stuff. So we have an infinite n, but your rule, let's see if we can just write this out in full right here without having to write the extra stuff leading into it. We're going from the first term to infinity. Your common ratio is 1/3. Your denominator is getting 3 times larger while your top is constant. That means when it comes to this rule, 1/3 to the first power is 1/3, and then you square 1/3 to get 1/9. You cube 1/3 to get this. You're raising 1/3 to whatever power you're dealing with here. In this sense, is the kth power. So to the first power, you get that, etc., and then you keep adding them infinitely to there. We'll talk about these more when we talk about infinite geometric series, but this actually converges, meaning if you added these over and over infinitely, it actually approaches a finite value. So the result of this actually isn't infinity. We'll talk about that when we get there, but just so you're aware. Because we're not evaluating these, right? We're not evaluating these. This is also... Well, actually, I don't know if this is geometric. Actually, it doesn't look geometric at all. This one has... It's like one of those special case things, if you can tell. The top's increasing by 1, bottom's increasing by 1, but they start from different places. So let's come up with the rule here. We're going from 1 to infinity as well by the ... part of it. If the first term is 1, then we can just plug in that k into right here. And then the bottom is having a common difference of 1, but that 0th term is 3. And it's important to stress we're plugging in 3 here, not 4, because... Or we have a 3 here, not 4, because if you plug in 1, 1 plus 3 gives you 4. So it would be that result there, and that's what we get. You might say, Mr. Robinson, you didn't use parentheses around that 1. Correct. Why not? Because this is all one term. This is all a single fraction here. But, Mr. Robinson, this was a single term or whatever. Yeah, but this was raised to that exponent. So if you saw an answer key thing, I'm sure this version wouldn't have parentheses as well. It doesn't hurt to use parentheses here. You just don't need them. Number 37. Oh, they're doing more of those special case things like these. Okay, this one is, I don't know if you saw the question before. This one's like number, and I'm only bringing this up because I'm not going to state everything about it again. This is like number 20 as far as what I'm going to do with it. If you look at number 20, make sense of it now or go back to it and hear what I want to say about it because I'm going to do this one like it. Because this one's like an arithmetic series. It's not actually because the sign changes. And notice that if we wrote this as a list of numbers, guys, this would be -3, +4, -5, +6, and -7. In an arithmetic or in any series, when you see a minus there, that means that the value of the term was negative because we're adding these lists. So for it to be subtraction means you're adding a negative. This is only 5 terms this time, so we are going from 1 to 5. I'm going to bring J into this. We're going from 1 to 5 on these things for J. Now, what we have to do with this is treat this like an arithmetic series. Just go with the whole common differences 1. The first term would have been 2, or sorry, the 0th term before this would have been 2 because you subtract 1 from 3, if these are all positive, like that. But there's another wrinkle to this in that if I want to make this term negative and then this one positive, etc., multiply it by -1 raised to the nth power. Oh, these aren't n's, these should be j's. To the jth power. That way, when you substitute an odd number into there, it stays negative. It turns negative. And then you raise this to an even power. It turns positive, like that. And that's how I would go about that one personally. Boom, boom. Okay. You can either put that in front or behind. That's up to you. Number 38. You might say, oh, this is one of those tricky ones. Actually, this one is a geometric series. These ones are multiplying by -2 each time. Now, once again, remember the list of this would have been -2, +4, -8, +16, and -32. Only 5 terms again, by the way. Not infinite. So from 1 to 5. And this one here, your first term, if you recall how these geometric sequences work, you do the first term times your common ratio, -2 to the n-1 power, you can write it that way. You can also, if you want to do the 0th term version, you can. You just have to divide this by -2. So this is an answer. Probably the one I would generally go with, but if there was a cleaned up version to be had, the first term was -2. So you could just do -2 to the nth power straight up. Oh, sorry, to the jth power. Shoot. I'm not even following my own thing. To the jth power here. You could do to that power straight up and all would be good. Because we're not doing to the -1, which means this is the first term here and the 0th term here of 1 exists in that. So either or is fine there. Okay, in 39 to 50, find the sum. This is where we are going to evaluate, but they start by not giving you what the terms are. So we actually have to come up with them. So this is honestly, I would actually probably have started with these problems if you didn't know how sigma notation worked when it comes to following the video. So you can then figure out how it works and why we write it the way we do. So what are we going to do here? We're going to substitute 1 for I into this rule, 2 times 1. Then we're going to add substituting 2 for I. And we're going to do this until we get to 6. Substitute 3 for I, 4 for I, 5 for I, and 6 for I. And these are the first 6 terms of that sequence. From 1 to 6, substituting them in. Obviously, we have to, compute them. And because it's a series, we're going to add them together. They said find the sum. Sum is series. And with that series, we evaluate. So this will be 2 plus 4 plus 6 plus 8 plus 10 plus 12, which is, by the way, an arithmetic series. And in the next section, you are going to learn how to do, this is a quick calculation, but you're going to learn how to use a formula to come up with these ones in the next section. At least I trust that's what they do for IM3. This should be 36, I believe, given what I know about that formula. 2 plus 4 is 6 plus 6 is 12 plus 8 is 20 plus 20 is 32 plus... Wait, did I do that wrong? Oh, I'm sorry. It's not 36. It's, yeah, no. I'm sorry. It's, 42. 42. I only saw this 12. It's 42. Let's try that again. 2 plus 4 is 6 plus 6 is 12 plus 8 is 20 plus 10 is 30 plus... Yes, 42. Okay. Sorry about that. Good thing I checked. Okay. Let's keep moving forward to number 40. All right. Now, if you notice what happened on the last one, maybe I can do a direct substitution without actually having to write that next thing. I'll say them out loud. But we're going from 1 to 5 for 7i. So we're going to do 7 times 1 plus 7 times 2 plus 7 times 3 plus 7 times 4 plus 7 times 5. Is that... Wait. 35, 42. Is that... 105. So let's see. 7 plus 14 is 20 plus 21 is 42 plus 28 is 70 plus... Yeah, so 105. Okay. Number 41. Now, this is not arithmetic. So this would have a completely different formula in and of itself. Here, we would directly just add. Now, we're substituting 0 first to begin with, and they actually used n this time. But keep in mind, they didn't have an original equation where they wrote out the things, so they're allowed to use n. I would use something different from the variable I established in the problem in these ones. Anyway, 0 cubed plus 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed is happening here. 1 plus 8 is 9 plus 27 is 36 plus 64 is 100. Now, the 0 had no effect on the sum. It doesn't mean that you can't do that. 42 has something interesting that I wouldn't mind bringing up in several ways. It actually technically would have applied to 39 and 40, so maybe I shouldn't bring it up. I don't think I'll bring it up because I didn't bring it up in 39 and 40, so I might go back to them and talk about them if I feel it's noteworthy. Okay. Yeah. I'll bring it up. I'll bring it up in a second. Okay. First thing we're going to do is 3 times... Well, you'll probably notice it here. 3 times 1 squared is 3 times 1. 3 times 2 squared is 3 times 4. Then we have 3 times 9 and 3 times 16. Now, what I was going to mention is all of these are multiplied by 3, which means the 3 can factor out. So we'll get into that version. You guys might just do 3 times this, 3 times that, and just work it out. That's fine. And that gives you 15, 42, 90. So here's an alternative version into what you can do, and this will explain away how this thing works. This 3 is a constant, which means this 3 can multiply by that sigma guy here. I don't want to confuse you on it, but that's how this looks. And you have the k squared, which means you can do 3 times all those k squared values, 1 plus 4 plus 9 plus 16. And that makes sense because 3 times all those numbers means a 3 can factor out from it. So you can do that there. Now, I could have done that for the first problems as well. I could have done 7 times 1 plus 2 plus 3 plus 4 plus 5. I could have done 2 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. And those are versions that we could have done for those previous ones if we wanted to. And it might be noteworthy to know these ones specifically because when we have to deal, what if we had to do the first 40 terms? Then I would use that quadratic formula that you had in the lecture portion and multiply that result by 3. So I think it's worth noting. That's why I decided to do it. All right, let's move down. Let's do number 43. Now, 43 doesn't start with 1. It starts with 3. But you do still go up to 6 from 3. So we have, this isn't the first 6 terms. This is terms 3 to 6. Which, by the way, how many terms are there from 3 to 6? It's not 3, right? It's 4. 3, 4, 5, 6. A little trick that might be important for a time when we write future rules. I don't know, but I know that I've done that in the past. All right, let's write these ones out. This is 5 times 3 minus 2 plus 5 times 4 minus 2 plus 5 times 5 minus 2 plus 5 times 6 minus 2, which is 15 minus 2 or 13 plus 18 plus, you can see it's a common difference of 5 if you want to do that, 23 plus 28. And that gives you 82? No, 82? I'm going to say 82. Good luck, me. All right, 82. And again, there were 4 terms. Number 44. N squared minus 1. I'll do these ones in my head this time, but obviously I'll write out the list. This is from 1 to 5 of n squared minus 1. And 1 squared minus 1, 2, whoops, I need a plus. 2 squared minus 1, 3 squared minus 1, 4 squared minus 1, 25 minus 1, and 36 minus 1 here. Oh, I'm sorry. This just goes to there from 1 to 5. Okay, sorry about that. All right. 3 plus 8 is 11, and then 26 and 50. Are they all like clean numbers like this? All right. Okay, number 45. It's a rational version of something. Cool. So we're going from 2 to 8. From 2 to 8 of 2 over I. You can notice, by the way, let me bring this up, when they used parentheses versus when they're not. When did they use parentheses? Only when there were separate terms. That's the only time. They never did it otherwise there. I would also, of course, use them in the instance of when you're raising to an exponent from a negative or a fraction, but in this case, no. All right, so we start with 2. So 2 over 2 plus, this isn't going to be fun because you got to work with fractions. 2/3, 2/4, 2/5, 2/6, 2/7, and 2/8. Yeah, I don't know if the answer we should write is I won't do a decimal because of repeated values, so we're going to have to deal with fractions, so this might take a moment. I want to reduce what I can because none of these are common denominators. That's 1/2. This is 1/3. And this is 1/4. At the very least, I can combine 2/3 and 1/3 right here. So that's 1 here plus 2/3 plus 1/3. I'm going to cross things out as I find them. 2/3 plus 1/3 is 1. So that's another 1 added. 1/2 plus 1/4 is 3/4. I'm just helping myself out a little bit. And then 2/5 plus 2/7. At that point, I have to kind of cave in and do like a common denominator. If I multiply this by 5 over 5 and this by 7 over 7, I get 14 over 35 plus 10 over 35, which is 24 over 35. So it looks like we're going to have to do some sort of common denominator stuff here. 1 plus 1 is 2. All right, so we're going to do 2 plus 3/4 plus 24 over 35. Okay. So a common denominator is 70 a multiple of... No. So let's just multiply this by 4 over 4. And this by 35 over 35. And 35 times 4, by the way, is 140. So we'll do 140 over 140 here. So here we'll have 280 over 140 plus 105 over 140 plus 96 over 140. Thank you for the problem, guys. 385 plus 96 is 481, so 481 over 140. Somehow I doubt that can reduce. All right. Cool. Number 46. Probably more of the same, but a lot less terms. In fact, there are only 3 terms. So, number 46, we have from 4 to 6. Notice they're using k. K over k plus 1. I guess we had k before. That's not new. That's going to be 4/5 plus 5/6 plus 6/7, right? I guess the numbers will still be big. I'm assuming the least common multiple of these 3 is just the product of all of them. And it should be, right? So multiply this by, I guess, 30 by 5 times 6, right? Multiply this one by 5 times 7. And multiply this by 6 times 7. Get a common denominator of 210. 210. So all of these will be over 210. It's 42 times 4 is 168. This guy here is 175. And this guy here is 180. So all these over 210 give you... I'm going to use the calculator. I don't want to mess up. 168 plus 175 plus... So that's 523. So 523 over 210. And 523 might be a prime number. I don't think it's going to reduce with that, so we'll leave it. All right, number 47. And all of these probably lean into a little bit of that the numbers are pretty big, so we have formulas within here to refer to. When you have... This is adding a bunch of ones over and over, and I don't think we need a formula to make sense of this one here. You're not substituting anything for I, but you are doing 35 of them. So you're doing 1 plus 1 plus 1 plus 1 35 times. So the idea behind this is for the number of terms you have, for the first n amounts of 1, the result is n itself, just 35 like that. That's all we have. That's the answer, and that should make sense. 1 plus 1 35 times is 35. Number 48 is you're adding 1 to 16 for the first n positive integer. Excuse me. You're doing 1 plus 2 plus 3 plus 4, etc., all the way up to 16. So that... ugly. So that formula for this in general... Give me a second. I'm having trouble. That formula in general, right? That's substituting 1 plus 2 plus 3 plus 4. You do n times n plus 1 all over 2, and those n's represent this value here of 16. So we're doing 16 times 16 plus 1 all over 2, or 16 times 17 over 2. 16 over 2 is 8. 8 times 17 is 136. Okay, now we're doing these just because it's quicker and we have the opportunity to do it. This one's trickier for it, though. Number 49, because this isn't for the first n positive integers. It starts from the 10th term and it moves forward. There is still trickery to do with this if you'd like to, because I'd prefer to not do 10 plus 11 plus 12 plus 13. There's actually another version I can do if I gave you the arithmetic series formula, but we're not there yet, not till next section. Here's what I would rather do with this instead. If we're adding terms 10 to 25, like 10, 11, 12, whatever, that means you'd be adding 1 to 25, but you take away 1 through 9. And that's kind of how I want to do this here. I want to do this setting it up saying that you're adding the first 25 terms, positive integers, and you take away the first 9 of them, and then you're left with 10 and 25. Does that make sense? You take away the 1 plus 2 plus 3 all the way up to 9, and then there's the plus 10, whatever, you take those away. And the reason I bring that up is because we have the formula only for the first n amounts of positive integers. So the first one here, that like n times n plus 1 all over 2, and then you're taking away this n times n plus 1 all over 2. And that should work it out, right? That should work out as that answer. Now, you can just clean up a little bit. 26 over 2 is 13, and 10 over 2 is 5. I know that one's 45. What's 25 times 13? What's 13 quarters? 325? So 325 minus 45, and that should give you 280. So was that faster than doing 10 plus 11 and stuff? Yeah, actually, I think it was. Maybe you don't write this out in full, or maybe you do. For me, I think it was. And listen, imagine if this was 250. I mean, how big does it get? I really do think they want you to practice some things like that for it. Now, number 50 is the first 18 square values. The squares of the first n positive integers. So there's another formula for that one, and it was provided in the lecture portion. It's something you probably have access to, but it's n times n plus 1 times 2n plus 1 all over 6. Given that our n is 18, that's what we're going to be using. Remember, that's only if it's specifically an n squared thing here. So we're going to substitute 18 into here. 18. And that's 18 times 19 times 37 all over 6. I am going to use the calculator here, but I'm going to divide that and get 3. So 3 times 19 times 37. That's 57 times 37. And that's going to be 2,109. Now, was that faster than the other way, the adding 1 plus 4 plus 9? Yes, it was. Use that when you can. Now, here's something I wanted to bring up. It didn't show up here, and it might show up in a bit, and I apologize if it does. But let's say that there was like a 4 here. This is where you could do what I was saying before, where you can take that 4, pull it outside, still do the same sum thing that you're doing before, and just multiply the 4 by all those. It can still exist in this version of the formula. Just pull it out before you get started, and you can use it. If there's a plus or something, or another term with n or something like that, you couldn't do it, but in this case, you could. All right, let's move forward. Numbers 51 and 52. On error analysis, we're only going to 61. I say only, but we're kind of almost done, I guess. Describe and correct the error in finding the sum of the series. The first one, straight up, you got to do 10 terms, and I only see 5 of them. Are they the first 5? Actually, I think they are, but they didn't do 10 terms. I don't know what to say. They're not done. They only added the first 5 terms. I would never see that mistake. That is kind of weird. I know why they did it. Maybe I would see that. I don't know. Not the first 10 terms. This was just happenstance why they did it. You know why I think they did it? Instead of doing it all the way up to, do you see it? Instead of adding all the way up to the first 10 terms, they added until they got a 10. Like to match this 10 with that 10. That's not how that works. It's not until the value is 10. It's until your position is 10, right? So you need to get to the first 10 terms. So for them, now I'm going to trust their math is right. They got 20 and stuff like that. So guys, let's just proceed on from that if that's okay. I don't want to write more than I have to. So 3n minus 5. So the first 5 terms added together add to 20. I hope that's okay. It's just a magic 20. And then the 6th term, substitute 6 into here. 3 times 6 is 18. Minus 5 is 13. By the way, this just means a common difference of 3. If you noticed, add 3 each time from the previous number. So let's keep adding 3. 16, 19, 22, and 25. So here are the first 5 terms. Here's the 6th, 7th, 8th, 9th, 10th terms. Let's just add these ones together separately from the 20, just because I feel like I want to. I'm having trouble. 29. 48, 70, and 95. And 95 plus 20 is 115. Okay. All right. So We have corrected the error. Number 52. Okay, number 52's issue, so they're using that formula of the sum of the squares of the first n terms or whatever. So you go to that 4, you substitute that in there. That's n times n plus 1 times 2n plus 1 all over 6. The formula's right. I'm sure their calculation's right. The problem is we can't use this formula straight up and use it for quadratic. Problem is you can't use it straight up because this isn't the first n terms. You have this I equals 2. We didn't start from I equals 1, so it's not the first number of them. You can use a version of it, but you got to subtract something out. They use the formula. They used a formula for the first n terms, but we do not start from I equals 1. I guess I'll say the first I terms. I don't know, because we're using I. We do not start from I equals 1. So what we got to do, and we did this from a previous problem, we subtracted anything that shouldn't belong, which means it's not going to be much different from what we have here. But when we, I got to fix my sigma. But when we do this I equals 2 to 4 of I squared, you can do exactly what they did here, but that formula is for the first 4 terms like this. And then you got to subtract the first term. So, which is 1 squared, which is 1, which means we're not doing much different. We just got to do 30 minus 1, which is 29. Now, let's see if that works. 2 squared is 4, plus 3 squared is 9. That's 4 plus 9 is 13, plus 4 squared is 16, and 13 plus 16 is 29. So that is the right answer. We're taking out the 1 squared because we got to, we don't have the first term there. It's not in there. All right. Number 53. You want to save $500 for a school trip. You begin by saving a penny on the first day. You save an additional penny each day after that. So we save 1, 2, 3, etc. It's going to take a while to get there. We'll get there. It's going to take a while. But you save an additional penny. Good. They give the example. I was going to say, for example, you will save 2 pennies on the second day. You won't have 2 pennies saved on the second day. Otherwise, that'll take 50,000 days. You're saving 1 more penny than the day you did before, and we're adding that. So our sequence looks like some sort of 1 plus 2 plus 3 plus etc. This is in terms of cents, in terms of pennies. Actually, should I write it? Let's do decimal values. 1 cent, 2 cents, 3 cents, and so on and so forth. Now we got to make this sum equal 500. That's now in terms of dollars, I think. How much money will you save after 100 days? Use a series to determine how many days it takes you to save $500. Okay. How much money you save after 100 days? The idea behind this is you can use summation sigma notation here for the, I'm going to use n this time, from 1 to 100 of the rule where your common difference is 0.01. And when zeroth term is 0. This is the rule we're going to be using for it. This is where I can use what we were talking. All right, you can do this one of 2 ways. Sorry. You can use one of 2 ways. You can either use this with 0.01 or you can use in terms of cents where you use 1, 2, and 3. I think they'd probably use the former, the other one. Sorry, guys. Let's go back to 1, 2, 3. The thing is about this, though, this needs to be 50,000 now. This is 50,000 cents. So let's just use an n here because now we can use that formula the way that you exactly know how to. The sum of the first 100 numbers from 1 to 100, literally. That's what it's saying. It's saying how much money will you've saved after 100 days. So this is 1 plus 2 plus 3, etc., all the way up to 100. But this is where you get to use your n times n plus 1 all over 2. So that's 50 times 101. 50 times 100 is 50. So this is 50. So you would have saved, and this is not dollars, this is cents. You would have saved $50.50. That's the important part about this. If you use that version, you have to know what kind of units you have. Okay. Now part B says, use a series to determine how many days it takes you to save $500. This is where we have to solve for n in this case. For what? Oh. Okay, hold on. Let's actually use I, because now I want to call this one n. You see, this is where I get a little messed up for myself. Let's go from I equals 1 to n. For what value of n will this rule give us 50,000 cents or $500? That's what we're figuring out. So on this side, we can do that formula. N times n plus 1 all over 2 and set it equal to 50,000. This is what we have to solve for. It's a quadratic. It's a quadratic. I can do a couple things here. I can multiply both sides by 2. And I can distribute n into here. N squared plus n equals 100,000. So n squared plus n minus 100,000 equals 0. I don't know if we're supposed to use use quadratic formula. I don't know if they'd let us solve using the graphing calculator or whatever, but that's, I'm going to use it, I guess. Quadratic formula, n equals negative, I got to sneeze. Excuse me, let me pause and drink some water here. Okay, sorry. Quadratic formula. Okay, so negative b plus or minus the square root of b squared minus 4ac. So that's 4 times 1 times negative 100,000. All divided by 2 times 1. Now, it probably won't be a plus or minus. We're trying to find a positive version of something, so I'm actually just going to use the plus. Just letting you know what formula I'm using for it, though. So, negative 1, I write plus or minus naturally. This is 1 plus 400,000 over 2. So, negative 1 plus that. All right, let's use the calculator for that and see it's probably not going to be exact. We'll see what they want to round to for this thing. Negative 1 plus square root. I don't think that 1 is making much of a dent in this thing here. Divide that by 2. We're getting 315.7. This is, n is number of days. So on the 315th day, we don't yet have the $500 by the 316th day. I guess we will. So to answer the question, how many days will it take until we've saved? That takes less than a year. 315.5, so that's about 316 days. Yeah, it takes less than a year. I mean, you don't automatically, it's not like the money comes out of thin air. You got to save it on your own, right? But you build that up over time, and it's interesting how quickly that builds up, because otherwise it would take 50,000 days just to do 1 penny a day. But if you add another penny over time, I mean, it builds. It does. All right. Number 54, modeling with mathematics. You begin an exercise program. The first week you do 25 push-ups. Each week you do 10 more push-ups than the previous week. I used to do things like this, where you'd ramp it up as you go and just say, hey, what's 1 more than the day before, right? And that's a good way to build some things sometimes. I don't just mean for push-ups. I mean for anything, running, anything like that. Any exercise stuff. That's a good way to go. So first week you do 25. Each week you do 10 more than the previous week. So I'm seeing this as how many push-ups will you do the 9th week? Justify your answer. I see this as, wait, are you just doing okay. I see this as a list that's like that, a sequence, right? Common difference is 10 more push-ups than the week before. Good luck if you can do that. I think that's pretty incredible to be able to do something like that. I don't know if you could. But you could literally just keep adding 10 till you go along. But I think the general thing is come up with the rule and substitute. Keep practicing what it is you need to practice for the big boys, for numbers that aren't so obvious. So here's my rule. Common difference is 10, and my 0th term would have been 15. You've probably seen that several times from me now. And they say the 9th week. So we substitute 9 into here, and we do 10 times 9 plus 15, which is 90 plus 15, or 105. So 105 push-ups on 9th week. That's what we're getting there. Justify your answer. I'll show you. In about 9 weeks, guys, I'm going to come back. I'll show you 105 push-ups. That'll be my justification for the answer. Number 55. For a display at a sports store, you are stacking soccer balls in a pyramid whose base is an equilateral triangle. Okay, so it's not a square base. It's an equilateral triangle base, okay? with five layers. Write a rule for the number of soccer balls in each layer, then graph the sequence. I'll tell you what, I'm guessing this sequence, remember when I said those numbers before were, well, depends on if you did the problem. It was number 20, this one. I said, I believe these are the triangular numbers. Well, these could be your soccer balls as well. This could be your first soccer ball on top. It could be on top of three soccer, they're not drawn like this, but it could be on top of three soccer balls. That's how triangular numbers work. They literally can be, they can be the numbers to build triangles. So your first thing has one soccer ball, and then there are three soccer balls, and then there are six soccer balls, right? It goes like this. This is why the triangular numbers are what they are. And then 10, and then 15. So that's the 5 layers. Like that. So 1, 3, 6, 10, 15. What are they asking? Write a rule for the number of soccer balls in each layer. Okay. Well, this isn't the rule, but this is the number of soccer balls, right? So this one here, we're adding 2, then 3, then 4, then 5, clearly. So it's a special case. And it's a quadratic special case because the second difference is constant. It's a different kind of constant, though. It's a smaller one. This would be 1 squared, right? But this isn't 2 squared. This is 2 squared minus 1, 3 squared minus 3, and 4 squared minus 6. So it gets a little weird and iffy to work it out that way. I'd have to come up with a different way to do it. I have to think about some sort of product I'm making out of it. So far, I don't know. Interestingly enough, let's see. Yeah, I have to think about how those rules work. Did we do a rule for this one at the time? You know, they came up with a rule here. Oh, well, that was a sum. That still works as a thing. Let's just use this. I was thinking it had to do with taking half of something, because I couldn't just use the 1 and keep it like that. And you're not multiplying by another number other than 1 unless you take half of it. So I'm going to go off of their thing here. I'm taking this. I think it's the same thing, right? So n times n plus 1 over 2. I mean, that's that sum thing of the numbers that we know. Maybe I'm expected to know that that's the sum of your terms. But so my rule can be like that for each layer, for that being the first layer. And let's confirm that it works. 1 times 2 is 2 over 2 is 1. Listen, we know it works. We did it before, so I guess we're good. They did say graph it, though. So 1, 3, 6, 10, and 15. I will take this graph stuff here. And no, I did. Copy, please. Will it copy? All right, good. All right. I can't really fit the 15 unless I change the scale. Let's go by 2s. 10 and 20. All right. 1, 3, 6, 10, 15. There you go. Okay. Number 56. Hold on. Let me make sure that was it for this one. Okay. All right, number 56. How do you see it? Use the diagram to determine the sum of the series. Explain your reasoning. Okay, cool. So like this is the first term, here's the second term, third, etc. They said it goes all the way to some 2n minus 1. The nth term has 2n minus 1. And, well, 2n minus 1 is the arithmetic rule. Like 2 times 1 minus 1 is 1, 2 times 2 minus 1 is 3, 2 times 3 minus 1 is 5. So that works that way. So as far as sigma notation goes, this would literally look like we're going from 1 to n of 2n minus 1. Like that, or 2i minus 1, excuse me. 2i minus 1 here. And I would know how to do I would know how to do it if I do. Okay. I have a version that I know I want to do. I'm trying to think if there's a version that they would want you to do without knowing what I know. Because these numbers are not the sum of the first n positive integers or the sum of the first. You know what? They're the sum of the first odd numbers. You can't take out the evens and... Okay, there's a way I can try and do it that would work best for what you know at this point. I don't know if I'll get the exact answer because I got to think about discounting the last number. This might get a little tricky, okay? So just go with me here. Oh, the sum of the series. I'm sorry. Let's just do this. Because those are odd numbers, 1 plus 3 is 4, right? The sum of the first two, I'm sorry, I was going to do something way bigger than that. Okay, guys. 1 plus 3 is 4. Hear out these numbers. There's 1. 1 plus 3 is 4. 4 plus 5 is 9. Plus 7 is 16. Plus 9 is 25. These are squared values. So the sum of the series, once we get to that 1, and this is based off this being the first, second, third, fourth, and we know that based off how many things there are, and this goes to n. So this would go to n squared. This will be n squared because each section represents that number in the series. So 1 squared, and then 1 plus 3 is 2 squared. Okay, I was going to do something significantly bigger for it. I was going to do one thing that you would be able to know by the next section. But we're not in the next section yet. And then I was going to do something way off the books. I would have gotten to n squared, but it would have been really weird. Okay, I got to start thinking in terms of the book more, not in terms of what I know. That's the problem. Or what I can do. All right, number 57, making an argument. You use a calculator to evaluate this because the lower limit is 3, not 1. Your friend claims there's a way to use the formula for the sum of the first n positive integers. Is your friend correct? Explain. I don't know. Okay. I know the answer because I already even said it with you guys before. I don't know when they say that for the sum of the first n positive integers because we're not doing the first n. We're taking out some of the first n. Oh, there's a way to use the formula. Yes. Okay. Yes, there is a way. Now, what we got to do is subtract 3. Not 3. Subtract the sum. Oh, yeah, 1 plus 2. So, yes, we subtract 1 plus 2 from the result of... And we would use this version here. So I did this for some previous problems where you do actually the sum of the first 1659 positive integers, but you take away the first 2 of them, right? This amount is 1 plus 2 plus 3 plus 4, etc. But we got to take away the 1 plus 2 because we're going to start from 3. That's how we do that there. So I'm going to leave it like that. All right, number 58. A regular polygon has equal angle measures and equal side lengths. For a regular n-sided polygon greater than or equal to 3, that's because triangles is the smallest you can have. The measure a sub n of an interior angle is given by this. I also agree with that. You may or may not know this information. These are all correct, and I just like to say, like, okay, I know what they're talking about. Write the first 5 terms of the sequence. Okay, so the first 5 terms of the sequence here, you actually start with 3, and each individual angle. See, you might know these already, but the sum of each individual angle in an equilateral triangle, equal angle triangle, is 60 degrees, and then in a square, it's 90 degrees. In a pentagon, you'd have to plug it in. Go and plug in 5. I think you get 108. And then in a hexagon, you get 120. These are just by memorization, just like I know them. I don't actually know 7 because I think it's a decimal. But, and I think 8 is 135. But anyway, I think those are the first 4, right? Oh, you do need 5. Shoot. Okay, I got to figure this one out. 180 times 5 over 7. Yeah, that's a decimal. So 180 times 5 over 7. I'm getting 128.57. I'm going to call it 128.6. 128.6. Okay, there's the first 5. That's part A. Part B, write a rule for the sequence giving the sum t sub n of the measures of the interior angles in each regular n-sided polygon. Well, I already know what it is. Can I just say it? I mean, you guys would probably know what it is as well. So t sub n in this case is just 180 times n minus 2. You ditch the over n part. You're not dividing by the number of sides there are anymore. So it's this formula. You just don't divide by the number of sides anymore. I don't know if I'm supposed to be using these in a greater way to get you that answer. We just know that's what it is. Anyway, I'm just going to use that. Part C. Use your rule in Part B to find the sum of the interior angle measures in the Guggenheim Museum. Oh, that's what that. I didn't know what that was. Skylight, which is a regular dodecagon. So in Part B, so t sub 12 is 180 times 12 minus 2. Yeah, this is an interesting problem set because these are numbers that we would have had. So this is the sum, by the way, 1800 degrees. These are things we would have been able to do back in IM1. I mean, they're asking the questions differently. If I asked an IM1 student right now, if they were in this kind of level of knowing it, find the sum of the angles in a regular dodecagon, this is what they do. Where did I get 10, by the way? I'm using this formula here, and I substituted in 12. So 12 minus 2 is 10, and 180 times 10 is, the 1800. All right, we have 3 more questions, numbers 59, 60, and 61. So number 59, determine whether each statement is true. If so, provide a proof. If not, provide a counterexample. And that's exactly how I would do a disproving. If I knew that something was false, I wouldn't try and prove it false. I would say, here's an instance where it doesn't work. Now, can I tell if these work or not? Depends on the problem. Oh, yeah, this one works. This is one I've been talking about several times. C is representing like a constant value. C is like 2 or 7 or whatever it is. And you can multiply that number on the outside of this thing. I could say it's true. And how did I support it? You factor it. So for the first n term. So the way that, okay, so this might look weird to you if you haven't done something like this before. So when you look at this one right here, remember C is a constant value. And C can stand for constant. But you do a sub 1 here plus C times a sub 2 plus C times a sub 3. And you keep doing this all the way until you do C times a sub n. And the bottom line here is C is a common factor in each term. So if you factor C out of here, then you do still have everything that's inside. C is a sub 1 plus a sub 2 plus a sub 3 all the way to adding a sub n. And is this not literally just what that is? That becomes C times the sum of the first n terms of your a sub I, from I is 1 to n of a sub I. So that does lead into that. This part leads into that, which leads into that part. So that is a proof of, oh, this is true, by the way. True. And yeah, that'd be the reasoning to me. Okay, letter B, we have I equals 1 to n of a sub I plus b sub I equals, and it splits up. Is that true? I guess it is, because they're like separate terms. I think this is true, so I'm going to go ahead and play support. I won't be able to come up with a counterexample if it's not true, but I can't think of something to counterexample it. Given my understanding of what I could do by plugging those numbers in with the set, given that it's a sum, that should be true. If it was a product, I'd say no. You're like, this was a product. Yeah, but this was a constant. This one doesn't change with I. This one just stays the same. These ones are a sum. I think that would work. So let's work that out, right? Yeah, this should work. So a sub 1 plus b sub 1 is the first one, substituting in, plus a sub 2 plus b sub 2, right? And this goes all the way to n, a sub n plus b sub n. Let's regroup these. Let's put the a's together, right? So this would be a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. Like that set. And then there's one for b's as well, just added together. Yeah, this totally works. So that, that becomes these two separate things. Let me just even copy it. Copy paste it. Oops, I don't want the whole thing. Never mind. So this would become the sum. This is the sum of the first n terms, or I terms, of a sub... No, the first n terms of a sub I. And this guy here is the sum of the first n terms of b sub I. So true. All right. Part C. Yeah, product. I don't think the product's going to work. Not for two things that vary. It's different. That's all I can say. It's different. So that means my understanding of it not being true means I want to go with the counterexample format instead of trying to prove something that won't be able to prove. So let's try it. I'm still kind of timid on what counterexamples I can do without getting too deep into this. Let's make a sub I be x, and let's make b sub I be x plus, or n, or I and I plus 1. How about? So let's try I equals 1 to n of I times I plus 1 and see if it's the same as taking those separately. N of I times... Oh, we have to actually plug something in. Let's try and go up to 3. So 3 here and 3 there. I plus 1. Okay, so we're going to see this one will be 1 times 2 plus 2 times 3 plus 3 times 4, which is 2 plus 6 plus 12, which is 20. This one, yeah, this won't work. This one is 1 plus 2 plus 3 times 2 plus 3 plus 4, which is 6 times 9, which is 54, which is not the same. So false. I don't know if I had to get that deep into it with trying it, but I tried an example, and yeah, they're not true. The next one's also definitely not true. I'm looking at it right now. Yeah, if I raise something to a power before or after I do a sum, oh, you know what? That's a good way of explaining it. Yeah, the product of a sum and sum of a product, like that kind of thing, it doesn't work out the same way. Same thing with raising something to a power. A sum of squares and a square of sums isn't the same thing. We know, like this, before I even write out this problem, guys, we know that a plus b squared ain't a squared plus b squared. That's a big no-no that we talk about all the time. So automatically, and hopefully you can recognize that's the kind of thing that they're asking here, that you take a sum of something and raise it. It takes some of things that you raise to powers versus taking a sum of something and raising the sum to the power. Not true. And I want to keep the example small. So let's try and keep it small. I'm just gonna call I literally. Let's do it for. I wonder if even for 2 numbers it'll work. Here's the thing: you might get a false positive. I hope not. Now to the C power, you can come up with that number. Let's say cubed. Let's see if we can come up with a false positive version. This is. We're trying to see if it's the same thing from going here to here of that and then cubing it after the fact. So this is 1 cubed plus 2 cubed, or 9. This is 1 plus 2. And then you cube the result. So that's 3 cubed, which is 27. That's not 9. So not the same. This is false. I'm sure squaring and stuff would have been fine. And that's the difference between the two. Okay. Number 60. Thought-provoking. In this section, you learn the following formulas. Oh, do we have to prove them? Write Write a formula for the sum of the cubes of the first n positive integers. So now we're going to do one that's cubed. I don't think they need you to prove it. I hope not. The way I used to prove these was using something called math induction, but that meant you already knew what the formula was. You know what might work here? Remember this problem here? Actually, literally, remember this problem here where we stumbled upon the fact these kind of added to n squared? These might... I don't think they'd give you this unless they added something nice. So the sum of the first n positive integers, 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, etc. If we go down here, 1 plus 8 is 9. 9 plus 27 is 36. This would have been 1, by the way. 36 plus 64 is 100. Oh, this has something. Hold on a second. How would I work that, though? Do you guys see what I'm seeing? This is 1 squared, 3 squared. The sum of the first one is 1 squared. The first 2 is 3 squared. The next one is 6 squared. So this takes the magic numbers, because these are the magic numbers, right? This takes the magic numbers and squares them. What was that formula? They used the sum of squares one. Oh, this is weird. So you square the sum of squared. Oh, how do I write that? So we'll say the sum. Oh, geez. The sum from. Oh, they have it right here. This one. You square this set. So from 1 to n of I cubed should be taking the magic number set that you get from there and squaring it. That looks weird, though. I'm going to clean that up. That's n squared times, I'll just at least do this, n plus 1 squared over 2 squared, which is 4. That's what I'm writing as the formula. That should work because that's using literally these numbers from that result to get that one out from what it is. I don't know if that's how I was supposed to figure it out, but it looks like it. Okay. Last question here is number 61. In the puzzle called the Tower of Hanoi... Oh, I have this in my classroom. And I even know the... Oh, shoot. Okay. I even kind of know the answers to this. So this sucks because I kind of already know the answers. Okay. In the puzzle called the Tower of Hanoi, the object is to use a series of moves to take the rings from one peg and stack them in order on another peg. A move consists of moving exactly one ring, and no ring may be placed on top of a smaller ring. Oh, I guess you don't need to know all the rules and what this looks like. Okay, the minimum number a sub n of moves required to move n rings is 1 for 1 ring, 3 for 2 rings. Okay, 1 for 1 ring, 3 for 2 rings, 7 for 3 rings, 15 for 4 rings, and 31 for 5 rings. Write a rule for the sequence. What is the minimum number? 6, 7, 8. The problem is, guys, I already know this answer. Like, I literally have this object, this thing in my classroom. I tell whenever students say, like, how long does it take to do this? I'm like, how many rings are you talking about? If it's this many rings, it's this long. And there's a reason behind it, and I wish I kind of demonstrated the whole thing. I could spend like 10 minutes talking about it, and I won't. We can literally just observe a pattern from here if you want to try. But what did I want to say? Oh, the only thing I want to say is this thing also shows up in the beginning of the movie Rise of the Planet of the Apes, where the ape is actually doing the thing, showing that the drug they're using is working. Anyway, guys, the thing that's going on here, this one's a little bit trickier. If you didn't know what was going on, unfortunately, I do. This is 2 minus 1, and this is 4 minus 1, 8 minus 1, 16 minus 1, and 32 minus 1. You may or may not recognize that. Now, they say write a rule for the sequence. 2, 4, 8, 16, and 32 are powers of 2. 2 is 2 to the first power. 4 is 4 to the second power. 8 is 2 to the third power, etc. So the term of the position is the power you're raising to, which means our rule can be a sub n equals 2 to the n and then minus 1. But the minus 1 is, down here. It's not in the exponent. And that's the rule that we can use for this thing. What is the minimum number of moves required to move 6 rings, 7 rings, and 8 rings? 2 to the 6th is 64. That minus 1 is 63 moves. 2 to the 7th, and that's how many rings I have on mine. 2 to the 7th is 128, and that minus 1 is 127 moves. I don't have 8 of them, but if I did, 256 minus 1 is 255 moves. Now, a student might ask, Mr. Robinson, have you ever done it with all 7 rings? No. Why not? Because I don't hate myself. I don't want to do 127 moves at minimum to make it happen. And really, there is a pattern to it as well. And it actually totally works with stuff that they're talking about on here. I guess I'm not going to get deep into the exploration, so I'm not going to. Guys, I'm going to cut off the video here. And that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Welcome to the intro of Chapter 7. I believe next comes arithmetic series talk. So get ready for that and then some geometric series. Take care. I'm going to see you in the next one.